In this video, I'm planning on talking about moving boundary work. This is also called just boundary work, or as we're going to see, this is also called pressure volume work or PdV work. So you'll most often hear this called PdV work, and so that's the moving boundary work. And so what this is let's say that we have a piston cylinder and we have some gas in here, and let's say that we have, so this is our system boundary here, this dotted line, and this goes all the way up to the piston. So let me redraw this up here. So then this piston is going to be moving up and down, and so what we have right here is a moving boundary. So we have a moving boundary in our system. And so that's why this is called moving boundary work. And we're going to see why it's also called PdV work as we go through the analysis. So basically, this will apply whenever you have an expansion or a compression of gas. And so an example of where you would have that is, say, a car engine. So in a car engine, the combustion gases force the piston to move. So we would have a combustion inside here of the gases, and they're going to force the piston to, well, when the gas is combusting, it's going to force the piston to move up, and that's going to force the crankshaft to rotate. So it turns out that with this moving boundary work, we can't actually determine the moving boundary work for a real engine. And what I mean by a real engine is an engine where the piston moves really fast. And basically, if the piston is moving really fast, that means that the gas inside the piston can't maintain equilibrium. Say that we have a piston cylinder, and we apply some pressure to the piston and push it down. So we're going to have gas in here that's at a certain pressure and temperature. And as we push this piston down, so we're forcing it down, so let's say that now it's down here, we're going to compress the gas and we change the pressure. So the pressure in the gas is going to change. This change happens slow enough, like let's say that this piston is pushed down slowly, then and it's so slow, like the slowness that I'm talking about, let's say that we have a pile of sand sitting on this piston, and what we're going to do is add a piece of sand. So we add a piece of sand to the piston, it pushes it down a tiny amount, and the pressure inside this gas, well, the pressure and temperature are going to change, and this volume change when we push the piston down happens so slowly that we can say that the pressure in the gas is still at equilibrium. So what equilibrium means is that the pressure everywhere in this gas is the same. So the pressure here is the same as the pressure here at the piston. So all of these pressures, like let's say we measure the pressure at different spots in the cylinder, the pressure will be the same everywhere. So then let's say we add another piece of sand. It's going to push that piston down a tiny bit more, and the pressure is going to change again, but we're going to assume that the change was so slow that it's still at equilibrium, so the pressure everywhere is still the same. What happens if we push this fast, like let's say that we're expanding and compressing the gas really quickly, like what might happen in a real engine, the pressure right at the face of the piston, so the pressure here, is going to be different from the pressure, say, down here at the bottom of the cylinder. And the reason why is because we apply pressure, so we're applying pressure at the surface of the gas here, and we're changing the pressure here, but the pressure down here might not be in equilibrium yet if this happens really quickly. And so what we can say is that, well, basically, so if we have a real engine, and a real engine would be defined as an engine with a piston cylinder, or that's having expansion and compression of gas that's happening very quickly. And so we can't actually determine the boundary work in those particular engines because the piston is moving too fast. And so in those engines, the boundary work is typically determined from direct measurements rather than from the mathematical relation we're going to discuss. So the mathematical relation that we're going to discuss, the PdV work, requires a quasi-static or a quasi-equilibrium process. And so these are both the same thing. So what this is basically what I was talking about here. We're applying the pressure, so the pressure is being applied slowly, or this piston is moving slow enough that we can assume that at each point as it moves down, so let's say it moves down, then it moves down some more, then it moves down some more, at each point of that movement we can consider that the gas inside that cylinder is in an equilibrium state. So what that means is, let's just draw a process diagram. So I'm going to draw the process for pressure volume. Let's say that we have, let's say we're compressing the gas from state 1 to state 2. So this might move along this process path like this. So what we're doing is we're changing the volume from state 1 to state 2. And if we say that this process is quasi-static or quasi-equilibrium, what that means is that every point along this path is an equilibrium state. So in other words, when we're right here, we're at an equilibrium state. So that means that the pressure inside the cylinder is the same everywhere. It's not higher at the face of the piston. So let's analyze, I'm going to draw another piston cylinder. So let's analyze a piston cylinder. Well, let's analyze gas inside this piston cylinder. And we're going to assume that this system is, that we're going to assume that this piston is moving slow enough that we can assume that the gas inside this piston cylinder is in a quasi-static or quasi-equilibrium state. This can be a pretty good approximation for real engines if the piston moves at slow velocities. So what I'm going to do, first of all, let's say that we have some force, and we have the area of the piston. So if we look at the piston face, we have the area, and we have some distance ds that the piston is pushed. So if we assume that this is a quasi-equilibrium process, then we can say that the work is equal to F ds, so the force times the distance. And remember, work is a path function, which means that it's an inexact differential. So inexact differential. And what this means is that in order to calculate this, or in order to calculate the work, we need to know what the path is. Equal to, so the force is pressure times area. So we have pressure times area, so that's the pressure here, multiplied by the area of the piston, ds. And area multiplied by this length is a volume. So this becomes PdV. So that's why this moving boundary work is often called PdV work. Pressure is absolute pressure, and it's always positive. So I'm just going to put this here. So this pressure is absolute pressure, and it's always positive. dV can either be positive or negative. So a dV that's positive, so dV, the change in volume, is positive during expansion. So positive during expansion. And dV is negative during compression. So this means that when the gas is being expanded, the work is positive, and when the gas is being compressed, the work is negative. Find the total boundary work during the entire process by integrating this relation. So this work is equal to PdV. And in order to calculate what the total boundary work is during the entire process, so remember the entire process, if we look at the PV diagram, let's say we're going from state 1 to state 2, the entire process is the work done along this curve. And so we want to integrate this to calculate the total work. So if we integrate this, the boundary work is equal to PdV. And remember, the only reason we can do this is because we're assuming that our gas, or that our system, is in a quasi-static or quasi-equilibrium state. So in order to evaluate this, we need to know what the relationship is between the pressure and volume. In other words, pressure is a function of the volume, and we need to know what that relationship is. So this relationship, if we have a quasi-equilibrium or quasi-static process, is simply the equation that represents the process path on the diagram. So in other words, we have, like if we go over to this PV diagram, we have this process path, and I'll just label that. So this is our path, and so the pressure is the equation that represents that path. So let's look at how this would look like. I'm going to draw a piston cylinder like this. So let's say we have a piston cylinder, and let's say that we're expanding the gas. And let's say that if we come down here, so this is V1, so that's going to be here, and then we have state 2, so here's V2, and that's going to be up here. We look at, let's just look at a volume across where, like let's say that the piston moves from here to here. So we're pushing on this piston and it moves from here to here. So we can call this, so this is really the change in the volume, so dV. And if we look at that on this process curve, so if we go up to here, this here is just an area. So this area is, so the change in area, this is equal to the pressure multiplied by the change in volume, so PdV. So the area under this curve is equal to PdV. So what we can do is we can say the area under the curve on the process diagram is equal to, this is state 1 to state 2, dA is equal to state 1 to state 2 PdV. We compare this to the boundary work, like this equation that we have up here. The boundary work is equal to, if we go from state 1 to state 2, PdV. So in other words, the area under this process curve, so if we look at this entire area, this is equal to the boundary work. So the area under the process curve on a PV diagram is equal to the work done during a quasi-equilibrium or quasi-static expansion or compression process. So I'm going to write that. So the area under the process curve is equal to the work done during a quasi-equilibrium process. And remember, quasi-equilibrium is an assumption that we make if the piston is moving at a slow enough velocity. Since the work is a path function, I'm going to go to another slide. So because the work is a path function, let's draw another PV diagram. So let's say that we have state 1, state 2, so 1, 2, and let's say that we have, so we could potentially have different paths that we do this work. So let's say that one path we do this. So let's say that this is A. And let's say we do work like this on a different path. And then let's say that this is another path in the middle. So because the work is equal to the area under the curve, you can see that depending on what path you take to do the work, the boundary work or the amount of boundary work done changes. And this kind of makes sense if you think about it. Like, let's say that you're driving somewhere. Like, let's say that we're driving from point A to point B. And let's say that we get a map and figure out that the shortest way is maybe something that looks like this. So that's one path that we could take. But let's say that we want to do a detour. Like, let's say that we go all the way up here, maybe do something on the way, and then we get there. So you can see that we've done more work to get to go from A to B in the second path versus the first path. So that's why the amount of work done depends on the path taken. And this also is a good thing because if you think about, like, let's say that we have a cyclic device. Like, let's say that we have, so let's call this 1 and 2. And let's say that we go from here, so this is A. So I'm drawing the representation for a cyclic device. So a cyclic device means that our beginning and ending states are the same. So in other words, we're going to go from state 2 to state 1, and then we're going to go back to state 2. So if we go back to state 2 on this path, then the work net is the work done on process A. So let's say that so this is the area under the curve for A. So we have work A, and I'm going to say work net. The work done for that is the work that we did going from state 2 to state 1. And then we go back from state 1 to state 2, and the work done for that is the work under this curve. So the work net is equal to the work done during path A minus the work done to go to path B, or on path B. This is going to produce a net amount of work because the work done during the expansion is greater. So this is the expansion here going, so this is PV. So the work done during the expansion, or process A, or the net work produced during the expansion is greater than the work done during the compression, and that's path B. And so basically, if work wasn't a path function, we couldn't get work from any cyclic device. And so you think about a car engine or a power plant. These wouldn't work as a cyclic device if work wasn't a path function. If work wasn't a path function, the net work would just be 0. And so the difference is the work net, and the work net is the area in here. So this is the area between these two process curves is the net work. So because of this, one way that we can calculate the work from experimental data is if we're given, let's say we're given a PV relationship, like let's say we're given a bunch of data points for a PV relationship. So let's say this is state 1 and state 2 again. Let's say that we just have some data points for the relationship between pressure and volume. We can plot those data points, and then we can calculate the area underneath this curve for the work done. So the equations discussed so far are assuming that we have a quasi-equilibrium or quasi-static process. But if we don't have so let's say we have a non-quasi-equilibrium process, so non-quasi-equilibrium, we can still use this equation. So we can still use the boundary work equation if we specify that this pressure is the pressure at the interface. And what I mean by that is, let's look at our piston cylinder. So during a non-quasi-equilibrium process, the pressure is going to be different at the face of this piston than it's going to be at, say, the bottom of the cylinder. And so if we specify that this pressure is the pressure at the interface, so I'm just going to say that PI is the pressure at the piston face, then we can use this equation to calculate the boundary work. Lastly, because work is a mechanism of energy transfer, the boundary work, or the PdV work, is, so let's say that so during expansion, the boundary work is the amount of energy transferred from the system. So this energy might be transferred to a shaft or something else. If the boundary work during compression, this is the amount of energy transferred to the system. So amount of energy transferred to the system. And this makes sense because when we compress the gas, we're raising the pressure, and so we're transferring energy to the gas. And because energy is conserved, that means that the work needs to be accounted for. So for example, if we have a car engine, is the work from expanding gases, and it's used to, so let's say that we have a car engine, and let's say that when the gas is expanding, this boundary work is overcoming friction. So there's going to always be some friction between the piston and cylinder. So we need to overcome the friction between the piston cylinder. We need to push the atmospheric air out of the way, because let's just draw this piston cylinder. So let's say we're expanding, so it's being pushed up. There's going to be atmospheric air here that needs to be pushed out of the way. And I'm just going to specify here, this is the friction. So there's friction between the piston cylinder. And then we need to push the atmospheric air out of the way if we're expanding the gas. And then whatever we're using that work for. So in a car, we would be rotating the crankshaft. So rotate crankshaft. So let's say that this is attached to like the crankshaft and it's rotating it as the piston is moving up and down. So that means that the boundary work has to be equal to the work from the friction plus the atmospheric work plus the work supplied to the crankshaft. And so this is equal to, if we go from state 1 to state 2, the frictional force plus the atmospheric pressure multiplied by the area plus the force from the crankshaft, and then dx. And this work from the friction, this appears as heat. So this is frictional heat. So it appears as frictional heat. And then this crankshaft work is the energy transmitted through the crankshaft to, say, the wheels and other components. This has been an overview of boundary work, or also called PdV work. Thanks for watching.